We have limited time and lots of ground to cover. So we're going to move quickly and live light on the land. So I'm going to start my slides, and we'll be going through a model that's available on the course site that's called SIRS model, ABM, and SD for alternative networks. Okay, so that's odd. It was up earlier for alternative networks version 5. And we are experiencing technical distress. So pardon me for just a second. I'm going to go and frob the requisite material. Okay. Okay. Good. Great. Thank you. Okay. Thanks for your patience. Okay. I want to talk a little bit more about networks. This is a subject that of which Wade spoke when speaking about some of the differences between agent-based and system dynamics models. But it's something on which I want to expand a little bit more here in the half hour that is afforded us. So networks form a key element in the repertoire of agent-based modeling. More deeply, they represent structure by which agents interact with each other and with the environment. Networks happen to be one of the main ways in which that structure is realized. There are other structures, like spatial structure. And indeed, one might imagine higher dimensional structure with things such as simplicial complexes by which sets of agents interact with each other. Not just dyadically, not just me and one other person, but like cliques of people, for example. And there's many reasons that we want to represent networks in these sort of structures by which that mediate interaction between agents. They can represent aspects of limited perception and limited awareness, the fact that I get information that shapes my opinions about vaccines or about the risks associated with some health concern from people right around me. There might be different dynamics, as we'll see, in terms of infection spread or spread of rumors or conspiracy theories across different network structure. And there might be certain changes to network structure, such as through the introduction of social media, that end up impacting it through those changes. There can be interventions that work via networks. A classic example would be for communicable disease would be contact tracing, right? That works by detecting for a given case, someone who's infected and known to be a case, who their contacts were. There are also many types of interventions like support groups or walking groups for physical activity that are some of the most effective around in their area. So a lot of interventions, when we wish to change things, work through networks. Perception works through networks. Influence works for networks. Risk spread can work through networks. Spread of innovation, ideas, knowledge, attitudes, beliefs, etc., can work through networks. And networks capture a structure that is at once not only important, but rich and varied. This is a graph I created when I wore a younger man's shoes about 20 years ago or so, no, 15 years ago, involving TB cases within Saskatchewan. And these clusters represent different communities. And you have, for example, some people spanning different communities that might bring TB or drug-resistant strain of TB from one community to another. So what is a network? Well, networks can be defined in many ways. Most classically, it's defined as a pair of a set of vertices and a set of edges. And if it's in accordance with many conventions, the edges are just subsets of all pairs of vertices. So this is a vertex, this is a vertex. So V cross V indicates pairs of vertices, one from here, one from here. And an edge from, say, A to B might be that person A has a link to person B. Right. A general form of network would have, okay, we have vertices and edges, and each edge has a source vertex and a target vertex. But for most of our attention here, for most of the presentation, we're going to be talking about undirected networks, okay? Where if A and B are connected, B and A are considered connected. Okay, so that'll be an undirected form of networks. Now, with that said, I mean, given the fact that most of you are coming from a computer science background, some of you will perhaps know through other courses that networks come in many forms. Directed, undirected, like to which we've just been referring. Situations where we can have more than one edge between people, or a situation where it only makes sense to have one edge. Like one edge from A to B might indicate that B is the mother of A, and it doesn't make sense to have more than one edge of that sort. In other cases, it could, right? A has had multiple contacts with B, or A has many types of relationships with B, different capacities in which they interact with B. So what we call multi-graphs versus single edges. There are things called bipartite graphs where you have two groups, and group A or group A and group B, and group A can only have contacts with group B, and group B can only have them with A and not within each of their groups. We can have weighted networks, etc. Right. We're going to be speaking here about a couple of the most iconic and important forms of networks out there. And what we'll see is that those structures, those network structures, those classic structures, induce dynamics. They induce behavior over time. And this goes back to the old chestnut that I've commented on in this classroom from the very first day, that structure drives behavior. Commonly, we use that to refer to the fact that the structure of a model, let's say it's stock and flow structure, or the state charts and their interactions or what have you, that shapes behavior. And that much is true. It can shape what's possible. If we have a susceptible infected recovered model and there's no ability to lose recovery, to have waning of immunity, to go back to the susceptible state, the number of recoverads can only stay the same or go up, right? Like there's no way it can oscillate, up and down, up and down. The only question is how quickly is it rising, right? And similarly, the number of susceptibles can only go down or stay the same, right? It's just in the nature of the structure. So we traditionally thought of structure driving behavior through the structure of the model that captures, as it were, our theory. But another key way in which structure drives behavior is through the structure of the environment in the networks. And we're going to talk about 5 major types of networks. 2 of them quite localized. That's in the bottom here. A ring lattice and distance-based. Here, two agents are connected if and only if they lie close to each other in some sense. We'll go to another extreme where two agents are connected regardless of where they're located. Willy-nilly, it's just with a certain probability. What's called Poisson randomness. And then we'll see that there's a middle ground called a small world network, which is a mix of those two, with the key thing being, the key fact being that even if you weave together largely local network structure, like 95% local, connected with people nearby, and just a little bit of global structure, just a little bit of connection to other random people that could be anywhere. It turns out that that shapes the behavior to be much more like a global situation. So in other words, there's a disproportionate impact of these global connections. Even though they're very few in number, in the proportion, they have way disproportionate impact. And that's a lesson we should take away. And then finally, we'll talk about scale-free networks as time allows. Okay, I will say that there's a generalization of networks we're not going to be talking about that is close to my heart and perhaps to Mehdi and PJ's heart, involving higher dimensional types of connections. And so these might be cliques between people, groupings of people, not one-on-one, but as groups. It might be a group of people sharing needles, or a group of people who study together, a group of people who publish together. And those higher level structures can be described not just with traditional graph. The best way to describe them is with what are called simplicial complexes. We're not going to talk about that, but they can be represented in agent-based models and can give some important types of insights. Okay, so I'd like you to make sure that you've loaded up this model. And as I say, time is short, and so we're going to have to go quite quickly in the next 20 minutes. But we're going to just take a look at each of these network types. And I'm going to try to use this as an opportunity to expand a little bit on the dynamics afforded by each type, but indeed to also give you an intuition for whence this comes. Okay, so we're going to take the same model, and this is a version of a model that Wade showed you from the seat not 3 weeks thence. And you may recall that each person in this model is in one of three states. This is our classic susceptible infected recovery with waning immunity. So it's an SIRS model because people can go back. And people are put in space. But we have reporting processes that will report not just on the ABM state, but another SD model running in parallel. And Wade really emphasized some of the differences there between them. We'll also see over to the right, not only that aggregate stock flow model, but a report on the number of connections that each person in the population has. This is a histogram. So each of these bins counts the fraction of people whose number of connections lie between one value and another. So if we see here 2, this bar, this would mean we have perhaps, just judging by this dummy data, 7% of people have between around 2 connections. Now, this is dummy data, so don't take that seriously. So what we're going to do first is we are going to examine a network which has people connected in a very localized fashion, okay? So what I'm going to ask you to do is go up to the very first experiment here and right-click on it and run it.
Okay. Okay, so this is taking longer than I expected to load. This is, here we go. Okay, I'm gonna press run there. Okay, so excuse me, this is unusually slow. I'm not quite sure what is going on here. Wait, any comments on?
Which this was the random thing?
No, this is the distance based. I mean, I've run it before. Here we go. Okay. So it may have been, it was just taking time to wire people up.
I think so.
Yeah. Okay. So if you scroll upwards here, what you should see is a vast field of people placed in networks. And each individual is shown with an anthropomorphic image. But what's notable is that we have people distinguished by their color. And there's enough people, to wit 10,000, that it's taking some time to sort of display this. But we're going to let this run here. You'll notice that there's an infection spreading, and there was a little bit of a slowdown there, which is unfortunate because it prevented seeing it spread sort of in real time. But you'll see it here spreading across this network. People's connections are shown in black between them. And you'll see it kind of sweeping here over different areas. I'm getting really laggy. Are you folks seeing it on your computer spreading? What are you seeing on your, are you actually seeing it visually spread? Oh,
Oh, really?
okay, maybe,
What is it?
oh. Aha. Yes, Aiden. Very laggy, yeah. Yeah. Okay. Thank you. Okay, so I think we'll just have to, that's really unfortunate. I think that's a version issue.
Maybe.
Aha. Okay. Okay, that's good to know. Okay, maybe I'll just comment on this a little bit. What we have here is a situation where infection starts at a single point and it spreads out from there. And as a result of it spreading, there's a wave of infection that grows. But that wave is mediated by the connections here. And those connections limit its spread to move locally across these networks. Yes. Nicola. Distance based. Yeah. 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 Okay. So you can see some initial infection down here. And we are seeing it spread sort of across the network. And does anyone want to describe, what do you see qualitatively based on what's on the screen? How would you describe that spread? Well, it's kind of spreading at any one point in a two-dimensional
almost wave, right? It's sort of where people are infected is really on the surface, the sort of the edge of this, right? There's a large group of people who are recovered in the center, but the active group at any one time is actually fairly thin. It's like you might have a certain area here infected, certain area recovered, and at any one point you have kind of this wave. And this is moving out, but kind of in irregular form because of the limits of the network and so on. So here it's spreading, and it picks up, it gets into pockets where the few people recovered yet, right? And it goes in there. It's very localized, spreads in a form that is fairly confined spatially, and is really sort of one dimension. So one dimension, I mean, it's like a ring here, or at least a sort of smaller, thinner area compared to the entire area of spread. You'll notice that over time, if people wane immunity, new areas opened up that were previously covered by recovereds, and there's the opportunity for spreading again. But the spreading can be blocked. I think it's the point which Pius made, or Nicola. I remember it coming from the Nicola Pius zone a few sessions ago, where the presence of someone recovered can block the infection spread across stuff. It can serve as kind of a bulkhead to prevent it spreading. Okay, so this is distance-based, and a key feature I want you to realize is it's localized. It spreads locally, it can be blocked locally, local obstructions can prevent it from spreading. I will note that if you scroll over to the right and up, you will see this histogram to which I alluded earlier. It's up here. And you can see that there's some disparity in terms of the number of connections of individuals across the population. Some having just a few connections and some having close to 15. Okay, we're going to stop that scenario. And we're going to go to a scenario which is equally localized, but actually is even more constrained. This one, we have this 2D area, this 2D surface over which the infection can spread. At any one time, it tends to be fairly localized, like on edges of this. But we have this 2D structure. Now what we're going to look at is a 1D structure, a one-dimensional structure. If you kind of zoom in at any one point, it almost looks like a line. And to do this, I'm going to need to ask your accommodation. I'm not sure how many people can actually run this model on your computers. Okay, a fair number. Okay, so those who are running it will want to pay attention to what I'm about to do. So if you go to main, I'd like you to go to the space and network area. And I'd like you to pick layout type ring. Okay. Ring. The ring of truth, forsooth. Okay. The one ring to rule them all. Okay. So now what I'd like you to do, having done that, so I went to main, went to space and network, chose under network type ring, and I'd like you to go to the corresponding scenario called the ring lattice scenario. And I'd like you to run said scenario. Okay, and what we're going to see here is, okay, I'm actually, in the interest of time, I apologize.
there's 2 ring lattice scenarios. I'm going to run the one with just 250 people instead of all 10,000. So it's this latter one, the final, well, it's a final one called baseline underbar. Baseline underbar 250 ring lattice. Okay. I'd like you to run that. And you'll see a smaller ring. In this case, what happened is that there was no material spread of infection at all. We just had everyone stayed basically susceptible. The first person recovered before it spread significantly. So we're going to stop this one. That is an aspect of stochastics. It is quite possible based on what happens. And now we see a spread that occurred across the network. And you'll notice the dynamics here. How would you characterize this curve for the number of sort of recovered over time going up and then down? What does that strike you? It's very what? So it's like a line going up and then going down, right? So the number of people recovering over time is not growing exponentially. It's growing in a way that is just sort of over time has more and more people in a linear sort of way, adding more and more people to the number infected before. This is the number infected at any one point. You notice the infection is spreading around the ring. That's all it can do. It can spread locally to neighbors. The ring lattice network has each person surrounded by some number of neighbors on their left and the right. I can't remember off the top of my head how many it has here. If it's 3 on the left or 3 on the right, or if it's 2 on the left and 2 on the right, Wade will tell us. But this leads it to spread around this ring in a gradual way. And this leads to dynamics, which are very different than when it spreads within the population in a less controlled way. The structure bottlenecks it. It constrains it in terms of to whom it can spread. And as a result, while it may spread across the population, it does so very slowly. In a way, this is even a more constrained version of the distance-based network. And that constriction, the strictures of the ring, limit the dynamics of how it spreads in quite profound ways. This is very different from an aggregate stock flow model where it can spread from one person to any other people, right? And you can get spread across the network very quickly and then recovery of people. Here we have it spread out. That given infection can spread out over a longer period of time because it's constrained in terms of how it can spread. So localized spread, whether it's distance-based or through ring lattice, even more extreme in 1D, leads to dynamics that are very different, dynamics that are spread out, dynamics where it can die out, where it cannot pass certain bottlenecks, etc., or it can be bottled in. Okay, we're going to go back to main and change that from ring layout back to random layout. So how did I do that? I went to main and I changed it under space and networks to random layout. Okay. So we've changed it to random layout. Now we're going to run so we've looked at 2 localized forms of spread. We are now going to go to random connections between people under baseline 10K random. And I'm going to right click and I'm going to run that. Okay, once again, it's initializing the network, so this is going to take a bit of time. And we will go and run this. There we go. Okay, so now we're going to have an initial infective, but they're in a network that extends across the entire space. In fact, it's so dense and so far-reaching that it's really hard to make sense. There's really just this tangled web of connections. Two people, A and B here. Previously, with the distance-based network, two people were connected if and only if they lay within a certain distance of each other. In a ring lattice, two people are connected only if they lay within a certain distance of each other. Here in 1D, on the ring, here in 2 dimensions. Now, two people are connected with equal probability, A and B, regardless of where they are. And it leads to this kind of crazy quilt of spread of infection across the network, where infection can spread, hop across the network to its far reaches physically, and make its way very quickly to other people within the network. Any two people are located quite close within the network because there's no limits to whom I'm connected geographically. So chances are I know someone who might be just a few connections away from you. And you'll notice here the infection spread, as Wade pointed out before, largely mirrors what we get out of an SD model. This is system dynamics stock flow model up at the top. This is the random network, where you have two people connected with equal probability. Mind you, it's always the same people to whom you're connected, but you still get some broad dynamics that are pretty similar in terms of the infectives, for example, here, the infectives there, in terms of the susceptibles here, susceptibles there. There are some differences in degree. So that's random network. We're going to now look at a medium, a sort of a halfway component between the two. And I thought I had gone and created that, a small world. Pardon me, I'm just going to go copy one of these and create that. I was quite confident I had that, but evidently I'm wrong. This is a small world network. Small world network is going to have most of the connections. Wade, maybe you could tell me what fraction are local, and then the rest are going to be global.
Yeah, the small world is 10 connections, 0.95% of fraction.
Okay, so 0.9, so 95% of connections are local. 5% are with people further away. So to be clear, what this is saying, those 95% are just with people around me within this ring lattice network. 95% of my connections are just with people nearby. 5% are with people far away from me. Let's see the dynamics induced by this. Let's see the behavior resulting from this structure, reflecting the fact that we're now a minute over time. So I'm going to zoom out of this, and we can see that already the infection is spread across much of the population. Does this strike you as more similar to distance-based and ring lattice on the one hand, or more similar to random? Random. It disseminated very quickly across the population. And it's not quite as close to to the aggregate system dynamics model as a fully random network, but it is one that has the broad features of this. It's not constrained in this manner of slow spread that leads to this slow, leisurely spread out across the population over a longer period. It's not occupied in little clumps and little sort of the surface area of some area where it's infected and everything else is recovered. We don't see that at all. What we see is sort of a broad dissemination, which is reminiscent here of what we see in the aggregate stock flow model. And the thing I want to communicate to you, this is a key point, that 5% of connections that are global made all the difference. If it had been 0%, it would have spread like ringworm. Totally different. Just 5% makes a night and day difference, a qualitative difference, to make it very, very similar to a global map. So heterogeneity matters. Like those small number of connectors, though small in number, they are mighty in their dynamic implications. And I want you to remember that the small world network is a combination of very local ring lattice with very global, think Poisson random. Two people are connected with equal probability, but its dynamics, as long as it has even a small fraction, like 5% of its connections globally, its dynamics should be much more similar. And with those words, I will close. Thank you.